Hello, guys. This is 10.8. We're going to look at a different variation of power series called the Taylor or Maclaurin series. So before we get into the topic, let's take a quick look of the power series representation for the function f that we have here. Right. So as we can see that we have our usual coefficient of the series, and we have the center of the power series at a to the power of n. All right, so if we expand it, it looks like this, right? C0, C1 times x to the first power, C2 x to the second power, C3 x to the third power, and so on, right? And this is our radius of convergence, right? As we saw from earlier in the last section, we can use ratio or root test to check when does the power series converge for some specific x value, right? So what we're going to do is let's say I am going to evaluate the function at a, right? That means I'm going to have plug in a into all the x's. So I have c0 plus c1 a minus a plus c2 a minus a square plus, let's do one more, c3 a minus a cubed, and so on. And then you will see a pattern that when we plug in a, all the terms with x's, they're all going to zero, right? So zero everywhere, right? Except for the first term, the constant term, right? Which is c0, right? So from this point, we can say that, okay, if we evaluate the function at a, we get c0, okay? All right, next, let's take the derivative, right? So let's say I have f of x. I want to find f prime of x. So f prime of x, we just take the derivative of the original expression right here on the right, right? A bunch of terms for the power series. So when we take the derivative, c0 will become 0. So we have c1 plus 2c2 x minus a plus 3c3 x minus a square. And let's do one more, plus 4c4 x minus a to the third power, and so on, right? And you can see that basically what we're doing is we're doing the power rule for every term, right? Bring down the power and then decrease the power by 1. And now if we look at f prime of a, right, we're going to have c1 plus 2c2 times a minus a plus 3c3 a minus a square, and so on, right? And then we get something similar to earlier where we get a bunch of zeros um, with the terms that have x's in them. So here, what we have is actually equal to c1, right? So what we can say here is f prime of a is equal to c1. And we do see some pattern here, right? So with zero derivative, we plug in a, it's equal to c0. First derivative, we get c1. What do you think the second derivative is going to be? All right, so let's take a look at that. Okay, so let's go ahead and do that. F double prime of x. All right, so f prime of x is right here. Let's take derivative of that. We get 2c2 plus 6c3 x minus a plus 12c4 x minus a square, and so on. And then when we plug in a, we get 2c2 plus 0, 0, and 0, right? So those are 0 when x is equal to a, right? So we get 2c2, right? And that says f double prime of a is 2c2. But what we can do is we're actually going to solve for C2. So we're going to represent C2 as F double prime of A. Okay, let's do one more. F double prime of A over 2. Let's do one more. All right, let's do F triple prime. F triple prime of X will look like 6C3 plus 24C4 X minus A, and so on. Right? And then when we evaluate at f triple prime of a, we get 6c3. That means c3 can be rewritten as f triple prime of a over 6, but I'm actually not going to write 6 in this way. I'm going to write it as f triple prime of a over 2 times 3. Okay. And if you continue this process to get C4 and C5 and so on. So far we get C1. Let's start with the beginning, right? C1. Actually, let's start with C0. C0 is f of a. Right? C1 is f prime of a. C2 is f double prime of a over 2. C3 is f triple prime of a over 2 times 3. So following this pattern, what we'll get for C4 is f the fourth prime of a will be 2 times 3 times 4. And then C5, the fifth coefficient, will be f the fifth prime of a over 2 times 3 times 4 times 5. So hopefully you guys can see some sort of pattern here, right? And let's write out the pattern. So let's say if I continue on, I want to find Cn, the nth coefficient of the power series. That's going to be f of the nth prime of a over n factorial. Okay, I want you guys to take a look and see if this general form right here applies to what we have found, right? Let's take C3 for example. So n is 3. We are looking at n is 3, right? We are looking at triple primes and then 3 factorials down here. Okay, so that is the formula or the form for the nth coefficient in the power series, and we can use this to solve the coefficient, to find the coefficients. Now we can actually rewrite the c's of the coefficient of the power series in this form, right? In the form of Cn using the formula. So when we have a series that is written in this way, this is called the Taylor series of the function centered at A. Okay, we're using A as our center, right? And that's the Taylor series of f as center at A, right? So the Taylor series is basically when we use this formula or this form to determine the coefficient. Now, furthermore, we also have a Maclaurin series of the function f. So if A is equal to 0, then we call the series the Maclaurin series of the function f, right? So another way to say this is if Taylor series is centered at 0, at A equal to 0, it's called a Maclaurin series. Okay, so Taylor series is the broader form of this type of series, right? You can be centered at any point on the real line, and the Maclaurin series is the specific name when it's centered at 0. Okay? And then we can find the Taylor series and Maclaurin series for different types of functions. All right, so our first example, we want to find the Maclaurin series for the function e to the x. So Maclaurin series means we want the Taylor series to be centered at 0. All right, so let's write out what our series will look like. All right, so it's gonna be the infinite sum of f to the n prime at 0, right? Because we're looking at Maclaurin series over n factorial times x to the power of n. Now this would be x minus a to the power of n. Now since we're looking at Maclaurin series, it's centered at 0. Right? So a is equal to 0 in this case. All right, so let's just find out the first few coefficients. First, f of x is e to the x. F prime is also going to be e to the x, and f double prime is going to be e to the x, and so on, right? All right, so let's look at evaluating at 0. F of 0 is 1, and f prime of 0 is also 1. F double prime of 0 is also 1, and so on. Okay. Then we look at the coefficient, which is f of 0 over n factor over 0 factorial. Right, so that's 1 over 1, which is 1. F prime of 0 over 1 factorial, that's 1 over 1, which is still 1. F double prime of 0 over 2 factorial, that's equal to 1 over 2, right? And f triple prime of 0 over 3 factorial, that's 1 over 3 factorial, which is 1 over 6, and so on, right? Let's do one more. F fourth prime of 0 over 4 factorial, it's equal to 1 over 4 factorial, and so on, right? So basically what we can see is for the nth prime, f nth prime of 0 is always going to be 1, right? Because no matter how many times you take the derivative of e to the x, you also always get e to the x. And when you evaluate e to the x at x equal to 0, it's always 1. All right, but the difference is the coefficient has to be divided by the factorial of n. All right, so n factorial. So that will be 1 over n factorial. Okay, so let's write out the first few terms and see what we have. Okay, all right. Let's see. So e to the x is equal to 1, right, plus 1 times x plus this times x squared plus, actually I want to do a 2 factorial here, right? So 2 factorial. Right, and plus 1 over 3 factorial x to the third power plus 1 over 4 factorial times x to the fourth power, and so on. And hopefully you can see what's going on here, right? The nth term will be 1 over n factorial times x to the n, right? So in general, what we can do is we can rewrite this infinite sum as n going from 0 to infinity, x to the power of n over n factorial. Okay, and that is actually the power series representation for e to the x. Okay, all right. So basically what we did is we used the Taylor series method to figure out the coefficient for the coefficient of the power series for the function e to the x. And you can do this with any sorts of function that you have, right? Trig functions, log functions, square roots, radical functions, rational functions, anything you want. So this is a nice way to rewrite any function that you have as an infinite power series. Okay, and we'll look at some more example together later. But now let's actually look at when does this converge, right? So that's a power series, right? We have to wonder, when does it converge? When does it converge? Okay, so let's do a quick test to find out the radius of convergence, right? Using a ratio test, a plus 1 over a n, right? That's equal to n factorial. Sorry. So that will be x to the n plus 1 over n plus 1 factorial times the reciprocal of a n, which is n factorial over x to the n, right? Which is n factorial over n plus 1 factorial, x to the n plus 1 over x to the n. All right, so let's clear out a few things. All right, so that's gone, n plus 1 left, and we have an x left in the numerator. That gives us x over n plus 1 as n approaches infinity. And this actually goes to 0, which is less than 1 for all x values, right? So it doesn't matter what our x value is. By the ratio test, this is always going to converge, right? So the radius of convergence is infinity, right? It will always converge, right? So that basically sums up the Maclaurin series for e to the x. Right? And we are going to use this method to try out on a few different functions. Right? So let's take a look at a few more. All right, let's look at our second example. We want to look for the Maclaurin series for sine. Now, I've put the general form for Maclaurin series right here, right? It's a Taylor series centered at 0, right? So basically this is, again, what we're going to be working with. But let's just look for the first few n terms and see if we can find some sort of a form or a general form that we can do. All right, so first thing, let's look for the nth prime of the function, right? So, and when n is equal to 0, we're looking at the original function, which is just sine, right? Sine x. All right, and when n is 1, that's cosine, one derivative, and then take another derivative, that's negative sine x, another derivative, negative cosine x, and then n to the 4, that's sine x, right? All right, that's evaluated at 0. X equal to 0, right? And we're picking 0 because we're looking at the Maclaurin series, which is centered at 0. Right? Maclaurin is centered at 0. All right, so just plug in 0 and see what we have. Sine 0 is 0, cosine 0 is 1, sine 0 is 0, cosine 0 is 1, so negative 1, sine 0 is 0. All right, now let's put everything together. Let's look at the f nth prime of 0 over n factorial, right? So that would be 0. That would be 1 over 1 factorial, 0, negative 1 over 3 factorial, and 0. Okay. All right. And we don't have that many terms to work with, right? So let's take a look at what we can get from here. Is that notice that when n is even, everything is 0, right? Because we're looking at sines, right? So when n is even, all the f primes will be sine, meaning we will get 0 for that term. So the only thing that we can get that is non-zero, it will be from the odd number of n's, right? 1, 3, and next one will be 5, right? Let's do 5, right? When n is equal to 5, that will be cosine x. Cosine 0 is 1, and that will be 1 over 5 factorial. All right, so let's write out the first few terms and see what we have. All right, so sine x is equal to 1x minus 1 over 3 factorial x to the third power, right? Because n is 3, so x to the third power, and then 5, 1 over plus 1 over 5 factorial x to the fifth power, and so on. Okay. And then if you keep moving on, actually, let me write out the next term. The next term will be 1 over 7 factorial x to the 7th power plus 1 over 9 factorial x to the 9th power, and so on. Okay. So you can see that this is actually an alternating series with only odd powers of x. All right. Hopefully you guys can see that. So I'm just going to write out what the general form is going to be. Right. So it's going to be plus negative 1 to the nth power times x to the power of 2n plus 1 over 2n plus 1 factorial. Okay. So this is the general form for the power series of sine. Right? So let's summarize it. Sine x can be written as the infinite sum from 0 to infinity of -1 to the n, x to the n plus 1 over 2n plus 1 factorial, which will look like x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial plus dot 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 so on. Right? And the radius of convergence for this one is actually also infinity. Right? And we can try that using what we have here, this power series on the ratio test. Right? But I'll leave that to you guys. All right. And one thing you can check if this is correct is when x is equal to 0, sine of 0 would be 0, right? So we want to see if we plug in 0 to the right hand side, do we get 0? Notice that all the terms in the power series representation of sine, they all have x's in them, right? So when x is 0, everything is going to be 0. So that makes sense, right? This power series representation or this Maclaurin series representation for the function sine does work. It matches with the idea that we have for the actual function of sine, right? So what we have here is we represented a trig function, right? That's a trig function with some sort of polynomial, right? Infinite polynomial for that matter, right? Which is something really interesting, right? Because we are comfortable working with polynomials, right? Probably not as comfortable as trig functions, right? So this is another way that we can represent a trig function is using a power series or Maclaurin series representation. Now you can actually do this for sine, and I think that will be one of the practice that we can do on Zoom. All right, so let me give you a quick overview on some of the popular Maclaurin series for some popular functions. All right, so here are some popular Maclaurin series. Now, notice that these we actually talked about them earlier in power series, right? Now they actually were found the same. We can actually do perform Maclaurin series with what we just did with these functions, right? 1 over 1 minus x, 1 over 1 minus x squared, ln of 1 minus x, and arctangent, and you would get what we have on the right hand side. Right, so these are actually Maclaurin series or power series centered at 0, right? And these two, which we have done earlier, right? Maclaurin. Right, so these are from 10.7, and these two we did it in 10.8. And cosine x, right? I really want you guys to give that a try. I'm not gonna do this on the video, but you can actually find so many videos talking about the Maclaurin series for the trig functions. I think we will probably do this on Zoom session as one of our practice. Right? So these are some important Maclaurin series, and keep in mind that Maclaurin series again is just a Taylor series centered at 0. Right? So I know we haven't talked about any of the Taylor series, which is not centered at 0, but we want to start with the easy things, which is Maclaurin series, centered at 0, and then we will take a look at some other stuff. Now, of course, what we can do here is you can take a function and then change its center at slightly different values, and then we'll see something a little different. All right, so let's do our last example for this section. All right, you want to find the third degree Taylor polynomial for f of x equal to square root of x centered at x equal to 1. All right, so now we're looking at something a little different. The center is not at 0 anymore, it's at x equal to 1. And specifically, it's only asking us for the third degree Taylor polynomial. So the third degree Taylor polynomial, we usually denote it using a capital T and then a lowercase 3 of x. Right. So capital T means Taylor series expansion, and then we just want 3 of up to power 3. So power 3 means we want to get to n equal to 3, right? equal to 3. So we need to start with n equal to 0, 1, 2, and 3. All right, so let's do that. All right, and then we need to come up with all sorts of terms, right? The first one is, of course, f nth prime of x. All right, let's do that. So original square root of x, and the next one will be 1/2 x to the power of negative 1/2, and then do again negative 1/4 x to the power of negative 3/2, and then again positive 3/8 x to the power of negative 5/2. All right. Now we want to look at them evaluated at x equal to 1. Right. So let's see what we have. That's 1. That's 1/2. That's negative 1/4, and that's positive 3/8. Okay. All right. Now, last, we want everything to be over the factorial, right? So the general Taylor series looks like this: f n prime of a over n factorial times x minus a to the power of n. All right, so we have all these are the f nth prime evaluate a, and we want f n prime evaluate a over n factorial. All right, so basically take whatever we have here over n factorial. So that's 1 over 0 factorial, which is 1. 1/2 multiplied by 1 over n factorial, that's 1/2. Negative 1/4 multiplied by 2, divided by 2 factorial, that is negative 1/8. Right, and then last but not least, 3/8 times 1 over 3 factorial. So that's actually 3, so 1 over 16. All right, so these are your coefficients. All right, and then these are the coefficients of the series, and all we need to do is put them in add in the x minus a to the power of n. All right, so let's do that. The Taylor series third degree polynomial of x for the function radical x is going to be first n equal to 0, that's 1, plus c1, which is 1/2, and then first power of x, x minus 1, plus, minus 1/8, x minus 1 square, and then plus 1 over 16, x minus 1 to the third power. And this third degree Taylor series is an approximation, a power series approximation for the function radical x. Right? So we have a finite number of Taylor series, and we're using it to approximate the function radical x. Right? So top here we have a third degree polynomial, right? And we're using that to approximate a radical function. Okay, and let's see how well this does. Okay. All right, so here I have included T3, right, which is the polynomial that we just found, and then the f of x, which is the actual radical x. So you can see that between, what's there, about 0.5 to almost 2, we have a really nice approximation right here inside the green circle right here. As you can see that they're very close, right? But like when x is after 2, the T3 starts going up because it's a polynomial, and then we still have the behavior for radical x, which is just flattening out as x increases, right? And here we have some values, right? When we plug in 1.5 into the polynomial, we get about 1.22656. And the actual square root of 1.5 is 1.22474. You can see that it's actually accurate down to the 100th place, and then it's when in the 1000th place that we get a little off, right? And the error is 0.0018. in the thousands place, that's where the error occurs. So I would say that this is actually the pretty good approximation for Taylor series. So here is a problem for you guys to think about, right? What can you do to make a better approximation for this function square root of x? What can you do to the Taylor polynomial to get a better approximation for this function? Okay, so that will be our discussion for this week, right? And then you can take a look at some more details on Blackboard. But for now, this is it for 10.8. And thank you guys very much. And I'll see you next time.